Yeah, welcome to my talk. Also, hello from my side. I have a talk about anti-fragile cloud architectures, but cloud doesn't necessarily mean you have to run in a cloud. It just means hardware is disposable. This talk is about how to build anti-fragile systems and a differentiation between a robust and an anti-fragile system. And I got to this talk actually because I read a book which doesn't have anything to do with IT, so it's really not related to IT. It's a book called Anti-Fragile, and it's a concept of Nassim Nicholas Taleb. He's a former trader, actually, so there's no relation with IT. And he coined the word anti-fragility. That basically means anti-fragility is the next step to resilience and robustness. The resilient system resists a shock, but doesn't get better, so it stays the same. And the anti-fragile system gets better. And this is about this talk. So I will show a lot of robust and resilient things, but I will try to show how you can influence or make your system architectures anti-fragile by doing some sort of stuff or by using some sort of technologies or patterns, obviously. So the book has basically, it categorizes on three things, how a system can be designed. And this system can be everything in life, basically. So he provides a lot of examples like banking and all the other stuff. So there are three stages how a system can be, in which stage it can be. It can be fragile, it can be robust, or it can be anti-fragile. A fragile system has every time a post-traumatic syndrome. So if you have a fragile software system, somebody with one request, he can basically kill your software system. If you have a robust one, it probably stays the same. If you have an anti-fragile system, it has a post-traumatic growth. So that means it gets better. And we will have a look how it will get better. There's another example, is a centralized or decentralized system. So the book makes an example that if you have a centralized government, the likelihood that the state is not so stable like a decentralized is higher. So decentralized is, for instance, Switzerland, and centralized governments are big countries who are basically ruled by the main capital city. So there are basically these three stages. A few examples. Fragile is something that breaks pretty easy. And to be honest, and I also take that on my side, most of the time we build fragile systems. So you can see it. Most of the time you run something in production and something happens that is not expected. It basically breaks. And it breaks basically means your system just stops to respond to user requests. In a robust system, it stays the same. But a robust system doesn't grow. So it can handle a lot of load, but it doesn't grow. Some more concrete examples in real life. Banking, based on this book, is a very fragile system. We have seen that all on Lehman Brothers. So if one or two banks go bankrupt, all the other banks also go bankrupt because we have a high dependency between the banks. The airline industry is pretty anti-fragile. If one plane crashes, it's an example in the book, it's very unlikely that the other plane will crash because every plane is very independent to each other. And also in the airline industry, unfortunately, what happened 2 days ago, most of the time an error is basically taken, you do measures, and you try to avoid this error. So in general, taking into account, since the 1960s, flying is much more safer if you have not been in one of those planes which crashed at that time. So that's a good example about anti-fragility, how systems can basically get better. And if we talk, or if we apply that to the IT, what we do, what we design, basically we see something that we have an assumption. Most of the time we call that assumption kind of non-functional requirements. We try to guess how many users we have, what these users do. Then we try to load and performance test, all this kind of stuff. But in the end of the day, we are every time facing the situation that we have too much load, so more load than we anticipated. This can happen due to more users, but most of the time this happens due to failure in the hardware or some other failure in the entire system. The problem with that is that if I add more load than I planned, most of the time the response time will go down. And at some point, I'm basically having so much load on the system that the entire system just breaks. And we have seen that so many times in real life, even big shops and big sites. And how to deal with that? Basically, you can try to scale and make your system more anti-fragile. Scaling is one possibility, and there's a book of the PayPal founders. They say basically there's 3 ways to scale, so this is kind of a virtual scale cube. You can duplicate things, you can modularize things, and you can partition things. And you can, at some point of time, you can get to the top right corner an infinite scale, which is not possible, obviously. So infinite scale, at some point of time, even the biggest internet systems, they basically have their boundaries. But with these 3 strategies, modularization, duplication, partitioning, you can pretty much scale a lot with your system. So let's see 2 or 3 examples and see how anti-fragile systems can be combined with scaling. So if you have a normal system, you can basically start to duplicate things, right? So you have 1 server, you make 2. You have 1 database, you make a read replica of this database. The nice thing is you can basically scale your system, but the downside of this is you can only scale in very big steps. So you can, if you have 1 server, you add a second one. It takes some time to start the server, to provision that. And during that time, where you don't have the server capacity, your response time is pretty down. So how can you deal with that? The general idea is that the unit of scale is basically smaller. So you don't have 1 big monolith server, you have small services which you can independently scale. And this is modularization. So you start to break your services. You move from a monolith, you move down to small services, and you can scale those services like you want. So if you see that your payment is very slow, you could basically scale your payment service while keeping the account management service pretty stable. And how does now an anti-fragile system work? Most of the time, scaling was something which has been done over weekends or once with a new release, you added new hardware. The general idea is on an anti-fragile system, the more load you add, the more capacity the system gets. And one concept is autoscaling. So that basically means that the more load your system gets, and you can measure that after the load is there, so you can measure the network performance of the CPU, and then basically autoscale. Or you can predict it. So if you know, like Netflix, they do it, they know that at 8 o'clock in the evening, there is basically prime time, everybody's watching Netflix, so you can start your service already at 7. So there's predictive scaling or post-analytics scaling. And this imposes a lot of things on your system. So the first thing is to really be able to scale, you need to be a very small, fine-grained architecture. And the second thing is scaling, especially downscaling your app, also means you have to be stateless. There's no state. Your system have to handle basically that you shut down servers during operation. And here you can see the difference between a robust and anti-fragile system. A robust system, basically, you have 2 or 3 servers, and it can handle the load. It can probably handle 10 or 20% more. If you have a fully auto-scaling system, this system could even handle 200 or 300%, because the system gets better and better the more load you add. The third part is basically partitioning. So that basically means you start to just split your data centers at all. This is also something which haven't been done before. And this is, again, centralized versus decentralized. A centralized system in one data center or one region basically means if something happens, your system crashes. If you have a decentralized system, what in terms of Talib means you are more anti-fragile, your system is distributed across regions and it will not likely crash. Also that means when you load, basically, that you split the load and the likelihood that one system gets the bottleneck or one data center is reduced. So now talking about modularization, we'll come back to regions later. A big trend currently is that a lot of people call that microservices. A few people just call it services. It's quite interesting. The biggest companies that talk about services, they just talk about services. They don't say microservice. Microservice basically kind of guesses about the size of the service, but essentially it means you just split your architecture. And a good way to do that is basically going into the area or reading the book Domain-Driven Design, which is already around since 9 years, actually. But reading this book, you learn a few things about bounded context, and then you start to split your application. So we learned that splitting your architecture into a front-end layer and a middle-tier layer, like the EGB or the Java E enterprise architecture proposed probably 10, 12 years ago, was not a good thing. We learned that basically splitting on your domain is the better option. And splitting up is pretty domain specific. There are a few concepts you can learn. It's like I split my domain. This is a simplified healthcare domain. And there you can basically see their relations to this module. So you learn how the services interact. So they are partnering, they're a conformist, they are a shared kernel, so that doesn't mean you should split everything, and then the system runs. This is nice in theory, and this could basically start and make your system more anti-fragile because you can scale, but the main disadvantage here, and this is one of the biggest benefits and drawbacks, is that you introduce something, and this something is called network. And we will learn now in the next probably 30 minutes that the biggest issue we face, especially with microservices, is networking and all the problems around that. Because what we have seen here, based on your domain split, you start to extract services. Those services communicate over the wire to each other. And the problem is, all those statements that you see here are actually not true. I mean, just one question, the network is reliable? No, it's not. Your network can break at any time. Latency is 0, it's also not the case. So if a method call takes 5 milliseconds and a network call takes, let's say, 200 milliseconds, you have still a multiplier of 40 times. So even though the latency might sound very small, it's still way bigger than a local method call. And these are the network fallacies. Network fallacies, it's already coined by a few people out of the Sun team. And they say basically everything is wrong on this statement. So latency is high, network is not reliable, bandwidth is finite, the topology changes all the time, and it's not in your control, by the way. And one thing on the network that is the problem is the timeout. So when you start to work with networking, you have every time to think about timeouts. This is something you don't do in local methods, but this is something you have to do if you start to do networking, especially with microservices. Unfortunately, most of the APIs in Java, they don't force you to set timeouts. So whenever you work with the API, and I made all the errors I'm showing now, one is JMS. If you still do JMS and receive things, if you don't do a timeout, your consumer might listen hours on the queue and even might have lost the connection in between. The consumer might be stuck, so you need to use timeouts here. We have the same on HTTP. I'm going to show a live demo how you can basically fool yourself without timeouts on HTTP. So by default, if you just open a URL connection, you do the call, and if your server has some block, so is not responding, then it basically also kills your system. So you should basically set timeouts if you do HTTP. The same happens for databases. So if you have a database pool, most of the databases unfortunately still have a very bad default configuration, so that basically means you wait forever for a connection. So if your pool is exhausted, that basically means all your threads can basically block and does not reply anymore. So just to show you an example, if you have two services, which is fine, so I have a small demo, a price calculator, which calls a currency exchange service. And even if you have two services and you do it the wrong way, basically you start to introduce fragility in your architecture. So your whole system gets more fragile, even though you started with a good intent to make it anti-fragile, so modularize it so that you can scale it. Basically your entire system starts to get more fragile because you don't do the things the right way. So let me just quickly switch the screens. So I have an application which basically calculates quotes, so price quotes. And this application has the problem that there is a service in the background which is not replying very well because it takes too much time. And the problem is I have two services, so I have a price calculator and exchange service. So the currency exchange service takes too much time, obviously. And the problem is my requests start basically to queue up. So a few requests go very fast, But if my slow service is called, basically the requests are just stuck. So as we can see here. So now to simulate a bit the problem, I just stop my good service, and I'm just left off with a very bad service. And this service is pretty easy. It just does a sleep of, I don't know, 1 minute or something. So it just replies very, very, it just takes very long to reply. So if I now go back and try to do some other calls, you see my system is basically not replying. So my request, oops, this was wrong. So my requests basically just start to queue up. And just to show it to you, the problem that I have here is my threads. So my server is basically starting to get stuck because I have blocked threads. And the problem is this can happen immediately. So if one system basically is too slow, your entire system crashes. So now I just put a lot of concurrent requests, and you can see here basically all my threads are just dead. And this is the main problem. Sometimes one service might fail, and your entire system crashes. For instance, you have a payment service which takes too long because the external payment provider is not replying. In the worst case, your whole system just starts to crash. And the general idea is you should never do that, or you should try to avoid that. One practice is what I told already. So the server is essentially dead now, so I have to restart it. The thread pool is just broken now. The first thing that you have to do, or you have to think every time you basically are approaching the network, you should think about to set the timeout. So this is a Spring application. Just a second. This is basically I just used now the HTTP client to the request factory and not the default one. And here, basically, the first thing you have to do is just set a timeout. So just set it to 10 or whatever, small value, definitely. And if I now restart the server, then we can see that basically nothing is better. So I don't get the reply because this service is still too slow. But the good thing is my server just stays responsive. So if I now make a request, I get a read timeout. This doesn't help for this service, which is broken, but it makes the entire system more stable because now all the requests are basically not replied, so they all fail. But the good thing is the server is still responsive. So if there are other use cases, they will still run. And this is the first thing you should do. Basically, every time you go into the network, just think about how to set the timeout. Unfortunately, the API basically tells us a bit that, or the default methods doesn't force us to use timeouts, which is quite bad, actually. So this is one way. Another way is there are new programming ways or new ways to program. So reactive programming is trying to solve that by not using threads at all or by using a very specialized thread model. There's Spring 5. This is an example, working with monos and all the other things. I'm not going into the details of that, but there are other programming styles to basically solve those timeout issues. The main thing you have to do, basically, is configure the timeouts and test them. So what people don't do most of the time, they don't do that, is, for instance, to test their system when they start to not behave like it should. So you can add latency. So there are tools on Linux. There is Netim, which you just can install it as a package. And the first thing what you can do is basically you just add latency. Just add latency to your network card and see how your system behaves. So you should do that in the test environment. Go to a server, add latency, or corrupt packages. You can just drop packages and see how your system behaves. Does it go into timeouts? Doesn't it go to timeouts? You can drop packages. You can even block the DNS server. And this is something you should really try, and not just craft your software, install it, and then hope for the best. You should really try to inject failure into your whole system. We will learn later about that, how to automate that as well. So talking about timeouts, there's already a few people out there who has even written books about that. For instance, there is the Release It book from Michael Nygaard. Unfortunately, the title is pretty misleading. This book is about running your systems and not about releasing in the sense of continuous delivery or something. It's really about running your systems. And there are big players in the market like Netflix who has implemented patterns of this book, which I'm going to talk now and to see how those patterns help to make the systems more anti-fragile. As you have seen, I'm using quite a lot of Spring stuff in my demos. There is Spring Cloud who implements that. And the first pattern that Netflix basically implemented based on the book is a circuit breaker. Circuit breaker is something that basically makes your system more anti-fragile. What we have seen now is we have seen a fragile system with no timeout. We have seen a robust system with a timeout, so I cannot crash the system by just putting a lot of requests. But a circuit breaker is an anti-fragile thing, because it does more than just making sure the requests are handled very fast without timeouts. It also isolates services. So this is like in the banking area. So you have a lot of banks, and if one bank fails, all the other banks might fail as well, because you have a lot of dependencies. And this also happens on a system that we built, IT systems. We have a lot of dependencies between those modules. And this is called the ripple effect. So what we can see here on the red line, the ripple effect is if the impact is too high. So if one service fails, it could in the worst case crash your system. If 2 or 3 fails, it will definitely crash your system. And the idea is with a circuit breaker to basically reduce the stressor of your system. That means basically when a system crashes, it makes sure, or when one service crashes, it makes sure that the other services doesn't crash, but also if the service is back again, the circuit breaker makes sure that it ramps up very nicely. So that also your system basically is back in business again. And how a circuit breaker works, in the end, it basically just makes a timeout for every method you can do. So you can run a piece of code and the circuit breaker will either run that and your code will run in time, or the circuit breaker will just interrupt the call. And the circuit breaker will also make sure that if one system is not available, a circuit opens and basically no call is tried. So it also tries to protect other services by just basically bringing a lot of load to them. And the thread pool, what we have learned now, it's trying to solve that by using dedicated threads. So that basically means you are not relying on the Tomcat thread pool. So once a service fails, all the other threads just queue up and cannot be run, basically. You have own threads. Every command, every method runs in an own thread and isolates that. We're going to see that right now. It has a lot of advantages. So it isolates all the method calls into separate thread pools. But thread locals are used all over the place in almost all the frameworks, also Spring. And that makes things a bit more complicated because you have to take care about those thread locals. How do you handle that? If you use Hystrix, if you start to use it, the first thing you will recognize you are not authenticated inside a command because it's an own thread and the authentication object is not transferred. So there are different ways to solve that. The general idea of Hystrix is that it protects you as a second level so that you don't have to use timeouts everywhere. Or if you have an API which is very fragile and doesn't support timeouts at all. So the general idea is you have a method and you just put an annotation Hystrix command. And this annotation can also provide a fallback. So if you have a search and the search fails, you can provide a fallback that you get an empty result, as an example. And let's go back to my system. So let's go back to this very small example. So now I can basically revert the timeout again, just to show you how things work, and I can basically use an Hystrix command here without a fallback. That basically means whatever runs in this method, even if it takes longer, the default is 1 second, the circuit will immediately cut and just reply. So that gives you rapid feedback and makes sure that basically no thread pools are consumed. Just there is a very slow service in the backend. So let's start that. And if I go here, you can see it basically directly timed out. And the advantage is you can also monitor those things. So if I put a lot of load now onto that system, my Hystrix will almost not release any requests at all because it knows the circuit is open. So why should I try to call the service? So it reduces your network load, it reduces the stress to other services because it already knows everything will time out. So once I bring back the service, then basically the calls will be made. So this is also about anti-fragility. It's not just protecting yourself about failures, it's also making sure that you don't basically crash the other ones. So the next part to be more anti-fragile is a service registry. If you talk one service to the other service, you have a disadvantage because I call it a point-to-point connection. So one service knows about the other one, the URL. If you have a robust system, you can basically, you introduce a service registry. So the service doesn't know each other, but they go and ask a service registry about the other service. With the service registry, you can also get even anti-fragile. So there are differences in service registries. So a service registry basically allows me to replace services. I can use different versions at the same time. And the question is, what service registry do I want to use? There are different implementations, and they all aim to different goals. So there is this CAP theorem, consistency, availability, and partitioning. And depending on your requirements, you can choose if you want a robust service registry or you want a more kind of anti-fragile service registry. So there is Netflix, Eureka, there is Consul, and there is Zookeeper. Consul and Zookeeper tend to be more consistent, and Eureka to be more on availability. What does it mean? A good example is partitioning. So every system can partition at some point of time. You have two data centers, and they somehow lose the connection in between. So you have two partitions, two separate running instances of your service registry. And now the big question is, how does this service registry now act? It could go to the way that it still stays available, but it trade-offs consistency. So it says, I'm probably not consistent, my data, what I have, but I try to answer all the calls as much as I can. Or it goes to the other way and says, I go for consistency. So I probably cannot answer your call, but I make sure all the data is consistent. And this is basically on your requirements. If you go more for an availability-based service registry, you are definitely more anti-fragile because you can survive failures like partitioning. But for the trade-off that you might get old data. How does it Eureka? Eureka, if it gets in partitioning, in the end of the day, once the connection is back, it merges your data back again. And that basically means you might have stale data for the time where the partitioning basically happens. And this is something you have to think about. Use cases like partitioning, there are service registries like Zookeeper and Consul. They strive for consistency. So they try with read replicas and a lot of techniques to be available. But for the first priority is consistency. And Eureka really tries to be available and trade-offs consistency. And this is the question, what's more important for you? Eureka tries to be anti-fragile because it tries after the failure to merge the data and be even better. So talking about a service registry, you choose an implementation, and now you have to think about how to discover and call the services. And this is service discovery, so that goes along with the service registry. You can discover services through a DNS. So Consul and Kubernetes does that. So they provide you a local DNS server, and this DNS server basically fetches the service information from your service registry and does the call. The nice thing is your client doesn't know that there is a service registry in the back. It just calls a fake local DNS URL, and then it gets the handle to the service. The other way around is that you use a discovery client. That means your application knows that you have a service registry and calls basically the service registry and gets the service information. The last piece is server discovery. You have a new component. So why should you think about that? Because service discovery also means if your system is robust or if it gets anti-fragile. If your system knows locally about load balancing, you can even get into a state where you get better and to some degree anti-fragile. Let's make an example. If you use client-side load balancing like Ribbon, you can define how do you call the services. So I want to call a service, I'm a client, and there are different ways to call a service. So we see on the left side, we see there is round robin. And this is linear. So you call one service, and then you call the other one, then you call the next one, then the other one. There is one which is availability filtering. That is non-linear, because if one service fails, then only the other one is called. The third part is, or the third strategy is a weighted response time. This is non-linear, but the advantage of this weighted response time is your system gets better. So let's make an example, or let's see why a weighted response time increases your throughput. And this can only happen if you have a very smart load balancing, which is pretty efficient if it's on the client side, because there you have the measure, the end-to-end measurement of the response time. Let's assume we have 5,000 requests. We can have two strategies. We can have a round robin, and we can have a weighted average. And we can see that basically on 5,000 requests, if I use a round robin strategy, I make 2,500 on a fast service and 2,500 on a slow service. So because round robin is stupid, so to say. It just does one request on that, the other one on that. If we use a weighted strategy on the client side, so we measure the response time, and the service which is faster basically is used more often, because for a lot of reasons it can be faster. It can be temporary, but it can be persistent. If I use the weighted strategy, then you can see that the fast service serves 4,366 requests, and the slow service only 634. But the advantage here is the average response time is only 27 milliseconds. Because we are basically utilizing the fast service even more than the slow service. And this is to some degree where your system starts to get anti-fragile. Because a robust system would be more a kind of a round robin with some availability filtering. If a service fails, I just don't call the failed service, but I still keep calling the other ones. If I try to get into this anti-fragile thing, I really try to see at runtime that one service is faster, so let's use that service. To be really anti-fragile, talking about petitioning again, it's a big topic obviously, you can also do a combination. So in the first sense, you try to be as fast as you can. In the second sense, you try to be as robust as you can. So there is zone filtering as well, and you can combine them. So the general idea is, as long as you have a fast service, just use the weighted response time. But combine that with an availability filtering, which knows about zones. So you can say, for instance, if my service in Europe fails, please go to the US one. The US one is obviously slower because there is a longer delay in the line, in the internet line, but it's better than failing at all. And this is something where you can do on the load balancing side, you can pretty much basically make a robust system, so try to answer each request, but also make it anti-fragile, try to make it faster. Again here, start and try to use or try to inject failures all the time. Simulate heavy I/O. Just write on the disk into a service and see how your microservice architecture works. Burn CPU. So if you want to make a service slow and want to test if your weighted response time works, get into the service and just burn somehow CPU. There are a lot of ways to do that, to burn CPU, and see if your load balancing starts to basically cover those cases and still be fast enough. So these are a few patterns you should definitely use if you start to use distributed systems. Last one is API gateway. API gateway is basically, it tries to centralize things. So we have a fully decentralized system, but a fully decentralized system means you have a lot of calls and a lot of potential failures. I've done a lot of kind of consultings or reviews where I see that people tend to use, let's say, 4 microservices, and then they call those 4 microservices directly from their single-page application, so some kind of REST, Angular, whatever. The problem is that if you call 4 times through the internet, it's way more expensive than calling 1 time an API gateway. And then this API gateway basically tries to call all the other services internally. You could use patterns like hate OAS and HEL to basically also do referencing or hyperlinking on the system. But more importantly, you avoid or you reduce the likelihood of failures. Internet connections are even worse than your data center connections. So data center connections are already bad, but internet connections is basically the worst thing that could happen. And the general idea is, with more connections, especially on bad network, you're basically increasing the likelihood of failure. So try to use an API gateway, try to reduce your calls into the data center, because that basically allows or decreases likelihood that your whole system will fail at all. So this is about patterns, how to implement that. But the question is, how do you run those systems? So all what I've shown here is basically essentially used for running the system, because you can forget about all those patterns if you write a unit test and just want to see if my application runs. It's not needed, what I've shown here. Those patterns are all designed to run your system. And unfortunately, most of the people, and also myself, it's not just the other ones, are used to have some kind of testing before we go into production. We used to have some kind of load testing. That basically means you add some load to the system. We used to do some performance testing, so we measure the use cases and see how fast it runs. And we used to do some stress testing. That basically means if my system can handle 1,000 users, let's add 1,200 and see if it still can handle those users. The problem is, once we have tested that, we end up like this. So don't touch those systems and never do anything. So we kind of test them, and then we bring it into production, and then we just start to pray that they don't break. And the problem with that is this testing is pretty nice, but this is what this book also says, Nassim Taleb. There is every time a black swan. A black swan basically means it's something we cannot imagine. So if I do a load and performance testing or stress testing, I only test against something I can think of. And in reality, it's unfortunately not only in software the case. If you create a nuclear plant, they decide what was the heaviest earthquake it have been on this place. So the nuclear plant must basically be robust to handle that earthquake. But unfortunately, there will for sure be sometime there will be even heavier earthquake than all the ones that happened before. The same applies to IT. If you test with 1,000 users, because you had one time 1,000 users on your system, it might be 2 days later you have 5,000 users. So we tend only to test things that we can imagine. And Black Swan, basically the idea is that people before 1697, everybody was thinking there are only white swans, there are no black swans. Until somebody in Australia, it was a Dutch professor, discovered that there are black swans in Australia, and then they had to rethink the model. This is our big problem of all people in the world, including me. We can only think of, we can only design tests and all the stuff that we can see and what happened in the past, but not what happens in the future. And the idea is, with anti-fragile system, to do hormesis. That basically means you put stress onto your system so that over the time it starts to get better. A good example is the human body. So if you want to run a marathon next year, you should start to train now. So if you didn't train, the first time you run 1 kilometer, the next week probably 1.2, so your body gets better because you're hurting your body every time. You are showing your body that it needs to basically cover up with your ambitions to do sports. And the idea with hormesis is basically to pull back the stressor. So what we can see here is the improvement. If we add hormesis to the system, it gets better. If we add too much, basically your system crashes. If you have 10 servers, it's every time good to kill 1 or 2 of them and to see if your system still runs. If you have 10 servers and you kill 10, your system will definitely not run. And this is the idea of hormesis. Just add a bit of failure into your system so that basically the stressor can get bigger over time. It's the example on the book. It's in the beginning, you can only lift probably 40 kilos, but if you do it a lot of times, you can lift 60 kilos at some point of time, but you cannot lift 100 kilos. And that's the idea on the stressors. And there's a discipline on that. I think there's even a manifest. A lot of people are writing manifests, but it's called chaos engineering. And basically that means you are experimenting on a distributed system so that you build confidence on that. And how do you do that on chaos engineering? So the general idea is you start with the steady state behavior of your system. So I have 10 servers and I have, 100 users. And then you start to vary your real world events over the time. So you really start to inject, you really start to vary the events. You decrease the server, you increase them, you introduce a new data center, and then you start to run experiments in production. And then you start to automate those experiences. And this is really important. Most of the people, they just don't do it, but you have to do that. What I've shown here, adding latency to your system, do it in production. Don't only do it on test environments. I mean, you can start on a test environment to get used to it, but in production, you should corrupt packages, add latency, drop packages, kill your DNS server, and see how your system behaves. In production, you should definitely simulate heavy I/O, burn CPU, and see how your system behaves. You could do that manually on yourself, or there are frameworks and tools out there, for instance, Netflix with the CMN army. So there are there are different gorillas, and those gorillas have jobs. So there is, for instance, a latency monkey, there is a chaos gorilla. And those jobs is basically to introduce failure into your system and to see if your system still behaves correctly. The easiest thing you can imagine is the use cases I've shown to you, and those are supported. So adding latency, burning CPU, and all this kind of stuff is supported by the Simian army. But you can also kill entire server farms with that, or you can even kill the entire data center. This is what Netflix does. They have a pretty good article how they do failure injected testing. Once every 3 months, they kill a complete region. So they really kill Europe, they kill Northeast America, whatever, because they really want to test that their system runs if a whole region is basically killed. That happens because once Netflix was down, I think on Christmas or the day after Christmas, because Amazon had troubles on a data center and then they couldn't fall back to another region. So they learned as well the hard way that you need to basically test for region failures in the end to make sure that basically if a region fails, your system can cover up. Yeah, that's almost the end of my talk. I really tried to stick to the 45 minutes I got. Thank you. So are there any questions? I would be curious to hear. Yes, please.
For instance, if you introduce timeouts, like you suggested, but technically speaking, where this timeout will be applied? Will it be applied on some driver level that root connection will really be dropped after 10 seconds? So will it be applied on your Java level, and then this thread will be simply abandoned? So, I mean, to my understanding, I will close the connection, but in reality, I will not. I will just expose all low-level threads, and that's it.
Yeah. I mean, I think it's every time hard. As an application developer, I try to do the timeout where I can do it. And I'm still aware that there are a lot of timeouts underneath. It starts on your router, on the network, and all this kind of stuff. But I try to be defensive on what I do. as a developer and try every API I use where I know there is some network connection, I really try to think, does it provide a native timeout? If not, can I use a circuit breaker or something different? Even though there are a lot of impacts which are out of my control, definitely, yeah, that could happen, essentially. Connections are closed and open on the network layer, which we cannot influence, but we can definitely make the worst case on the timeout that if a connection is stale. Because sometimes, a good example is on the queuing, I had that on myself, the connection was already closed on the network level, and the method never comes back, never ever, because the connection is in a dead state, so to speak. And with the timeout, you really try to be only defensive on what you do, even though it doesn't guarantee you that it will work that way. Yeah.
We got 2 questions on Slido.
Yeah.
How to make service discovery at least robust? That would be the first question.
How to make service discovery at least robust? Yeah, you can use Eureka, which is robust. You can think about, for instance, Zookeeper works with the quorum. So you can think about what happens if partitioning happens. Because most of the service registries, then they just stop to accept changes, but you can still read from them. So you could think about what happens on partitioning. Do I really need to publish new services, or can I just stick with the old ones? But if you want to be robust, I would suggest Eureka, but you have to be careful that in the worst case, you might have some stale data, which is not so bad on a service registry, to be honest. There are worse cases, yeah, for that.
Okay, thank you. And another question, don't you think that service discovery itself is fragile, and how to deal with that?
Yeah. By adding a service registry, you make your system more fragile. You have one more component, you have one more network call, but those service registries, and the main important thing is you have one central component which could fail. So if you create a microservice architecture and you have one instance of Eureka, it's a pretty bad idea, because if that instance fails, your whole system over the time will crash. It depends how the clients handle the case that the service registry is not there. So in the end, it's a trade-off. You add fragility, or you make your system more fragile, but those service registries provides mechanisms and ways to make it, in the end, more anti-fragile. But every component you introduce to your architecture, every modularization you do, in the first place, they make your system more fragile. By doing the right things, you might grow with your system, but adding a service registry makes it more fragile in the beginning. Yeah,
yeah, thank you. Any other questions, guys?
Yeah, I've got a question.
Yeah.
So, could you give us like real life, so production, like example of circuit breaker stuff, so that okay, service doesn't accept data, where does the data go, what's happening then, stuff like that?
Yeah, there are different use cases for circuit breakers. The easier thing, which is quite easy to implement, is read use cases. So like I've shown, you have a search use case, you give an empty result. When you start to write, it's quite hard to do fallbacks, which are also good for your system, so they're consistent and everything. You could think of basically to do a live update. If the live update does not work, you can write into a queue, for instance, and then get those updates at a later stage. So if you do order processing or something. Unfortunately, you have to think really on a use case base. There are some use cases which works very well, and some use cases doesn't work very well. So almost if you think really hard about your read use cases, there is almost every time a good fallback you can do. And in the worst case, an empty result. You could query another system, you could retry or whatever. The right use cases are a bit more complicated. I would try to design my use cases anyway in an asynchronous way. Try to kill synchronous calls from the beginning. But if I have synchronous calls also to legacy systems I don't control, then a circuit breaker is a nice toolkit. But in the end of the day, there are architecture styles like event sourcing, asynchronous designs, which I tend to try to implement in the first place and use circuit breakers only for external systems I really need. Yeah. But in general, a synchronous call makes your system more fragile. If you can avoid a synchronous call, that's the better way than introducing a circuit breaker. So before the need to use a circuit breaker, I'm thinking of, is there a design I can do it in an asynchronous way? So for instance, instead of calling an order service, I just put the order into a queue, and then he should pick it up at some time. Things like that, on byting.
Yeah, I think we're running out of time. So thank you very much.
So I'm here the evening. Thank you.